Hi everyone. Today I'll be talking about democratizing machine learning model development process and just a bit about myself. Metas quickly, briefly introduced me, and I think that's what I wanted to talk about myself. So I'm a contributor to the Number project and also Titus 2, which is a portable format of for analytics implementation for Python 3. And I've been working in the industry, analytical industry for around 6 years. I started off as a data scientist, then move on to become a product manager, shipping product called as Analytics, which has around 600 functions. And so I've been basically working towards the model deployment process for a lot of companies and how to basically make the model development and deployment cycle faster. So that's my core focus for the years. So we'll quickly start with the talk. So let's start with the first thing that I like to talk about, which is evolution of analytics. So I'll be talking about how analytics has evolved over the past years or decades, let's say, and how we have brought together analytics closer to the data source. So when we first started with analytics, it was basically dedicated machines. So we had dedicated machines like dedicated servers, analytical servers like SaaS servers, where people will go and perform analytics, run their codes on the data and get the results. Then over the past 2 decades, the cloud has emerged and people are now running basically running on public and private clouds. All their analytics have been run on the public and private clouds. Then came the era of fog, where basically for example, let's take an industry. It has a lot of sensors and a lot of robotics and basically different kinds of sensors. Yeah. And to manage them and to basically interact with these sensors and they basically run the model. Usually they have a network, internal private network, where there is a single analytical server, which is called as a fog. So this server is not connected to the cloud, but locally it is like a cloud for the local group of sensors. So that is called as a fog. So the fog emerged where people were started bringing the analytics closer to the source of the data capture process. And today now we have completely moved to the edge. So a lot of the new devices have analytical engines embedded in them. And so basically we are trying to capture the data and process them at the source of data capture. So that's called as an edge. So this is how the analytics has moved towards. And let's move on to the next segment. And a major reason of moving towards the edge was that today it is approximated that there are around 50 billion connected devices. So these many devices, you cannot capture, send the data to the cloud and basically process them. So bringing the analytics closer to the edge enables these 50 billion devices to process the data and basically run the models. So now let's talk about what is the need of edge analytics. So why is the cloud no longer sufficient? The first and foremost thing is speed. So when you perform analytics at the edge, there you gain the speed that there is no latency. You are not transferring any data to the cloud and waiting for the data to be processed and then getting back the results. You are processing data at the source itself and deriving some valuable insights, which is basically we perform analytics to get some valuable insights, and that can be done at the source itself. So that's why you gain a lot of speed. So that's why you move towards the edge. And next thing is cost. Running these cloud servers puts a lot of load on the data transfer process. As you can see, there's a cost of data transfer involved whenever you deploy your models on the cloud. So it saves a lot of cost because you can process the data at the source itself and basically save only the valuable insights instead of saving the entire data, which will take a lot of space also on the cloud and also a lot of network and bandwidth cost. So you save a lot of cost by processing data at the source. Again, next thing is connectivity. So A lot of countries, developing countries, they don't have the internet connectivity which is so good that you can transfer gigabytes of data to the cloud. So and also there are a lot of locations, remote locations, where you want to deploy analytics. For example, this windmill that you see, so there are islands which have windmill, and they do not possess the capability to basically connect to a network and transfer the data to the cloud. So you want to keep your analytics. So for example, for this windmill, you can have uh, basically wind turbine, you can have a model which is deployed locally, which will process the current state of all the health of the wind turbine, the health, the other stats basically, and basically tell you that okay, the it is functioning really well, and you and or if you need to do some maintenance to as some parts are failing, so these things can be processed locally. And that's the reason why basically the kind of low connectivity can lead to companies and firms explore the modern deployment process at the edge. And last but not the least, privacy and security. This is one of the major concerns that a lot of data which basically the users want to know that okay, are their data going to be transferred to the cloud and stored there for how long, and basically what valuable insights are the companies deriving from that data, are they selling that data. So these are some important privacy concerns which users nowadays have, and they want their data to stay with themselves. So a lot of companies are pushing towards moving towards the edge and putting their analytics model on the device itself, so that the data is private and secured, as they are not transferring the raw data to the cloud, and only the valuable insights, as in what is the for example, for products like Fitbit or Apple Watch, only the healthcare stats, like is the user facing is there some health issue which is going to basically haunt the user later on by processing his blood oxygen level or basically ECG, instead of transferring the entire raw data. So this privacy and security concern is one of the major reasons why companies are pushing towards the edge. So let's elaborate on some of the use cases. We all are familiar with the rise of basically autonomous vehicles, and so transportation sector is one of the core sectors where analytics is performed at the edge. As you can see, there are a lot of sensors like long range radar, lidar. There are cameras which are generating tons of images, capturing tons of images. Then there is different types of range radars, and approximately 1 Gbps of sensor data is generated by an autonomous vehicle. And this such huge amount of data is not, it is not possible to transfer it to the cloud and then process, and by the time they receive some actionable insight, uh, it is too late. So that's why you have to deploy cutting edge model at the edge, which is in the vehicle itself. So this is one of the major sectors which is using it. Then in healthcare, as I discussed, Apple Watch, Fitbit, these kinds of devices, they now have their analytical engine built in the device itself, so that it can give the user, it can give a quick feedback to the user that okay, is he at the danger of an heart attack, or is there any issue with the health. So there are a lot of other devices also which are available in this sector, which process the data, raw data quickly, and inform the user about any actionable insights. And obviously there is manufacturing. So there was first industrial revolution, second and third industrial revolution, and right now there's another revolution going on, where a lot of industries, manufacturing sector, and also warehouses of e-commerce, they are deploying a lot of robots and basically systems which have analytics inbuilt in them, so that they can perform basically the tasks and the processes efficiently, and increase the throughput of the firm. So it is majorly used in manufacturing nowadays. So now let's move ahead to the analytics life cycle. So we will talk about what is the analytics life cycle. And it is basically any analytical process can be incorporated into this life cycle. which starts with identifying the problem. So basically, you identify the problem. What is the problem that you're targeting, and then you access the relevant data, whether the data resides in a SQL database or it resides in a simple CSV file or some other basically on the over the web API. So you go ahead and access the data, then you explore the data, do some initial exploration of the data using some of the toolkits in Python. There are some toolkits in Python which help you do that. You do some initial plots and calculate some initial statistics and explore the data. Then you pick the right variables, features, which are relevant for your model building process through filtering and transformation of the data. Then you actually go ahead and build the model. This is something which excites everyone, which is building a model and basically seeing their entire process in action. Then you evaluate the model. We use a lot of methods to evaluate the model, like uh, k-fold methods and other methods, accuracy to evaluate the model. And then starts the process of actually using the developed model to get some actual insights by exporting the model, deploying it, then monitoring the model, how it is performing. Is it performing as expected on real life data sets of the users? Is it evolving over the time? There might be cases where your model is degrading with time, it is not up to the mark, so you monitor the results. And then you manage the model, basically versioning, model versioning, how to update a new model. And basically those parts come under the managing model management part. And then after managing models, monitoring the result, you can stumble upon a new problem and the cycle continues. So this is an important analytics life cycle which defines all the key aspects involved in starting from identifying the problem to deploying the model. So most of the talks you might have started with identifying the problems and finished it off with evaluating the problem. But what happens after it? So okay, you developed a model. It is giving you 99% accuracy on the test data set. Great. Now what are you going to do with it? How are you going to deploy it? So these are some of the key questions that we need to ask, that how it actually happens in real life and in firms. So then we come to the next part, which is democratizing model deployment. So what do I mean by it? Is basically democratization of model deployment is giving the choice to the model developer that how he wants to deploy his model. So that part, whether he wants to deploy it using a particular infrastructure or a particular framework. So giving that choice to the developer, it's called democratization of model deployment. And let's take a hypothetical company X. In that company, there's a data science team, and there are data scientists spread across the globe, and some are proficient in might be proficient in TensorFlow scikit-learn. Some might be proficient in R/S2 AI. Some might be proficient in Keras PyTorch. So, and some might be proficient with some Java libraries like Vika and Spark ML. So data scientists have their own core competencies in terms of, or preferences in terms of programming languages, toolkits and frameworks through which they develop their models. And suppose these four data scientists, they come together uh, to solve a problem. They develop individual models, M1, M2, M3, M4 as seen, and then send it to the basically the IT DevOps team to deploy it. So what happens next? So this is what happens. People wait. They are like, okay, why isn't my model deployed? So the DevOps person says that we are coding it in C++. Then the developer says that, okay, we can just containerize it and orchestrate. And the DevOps team is like, no, we cannot do that. And basically, we all have gone through conferences a lot of and heard it in tons of conferences that why don't we just do containerization and orchestration? So this is a major sector which is growing, and a lot of people talk about it. Okay, like, why don't we do it for our company? Why don't we just develop it and ship the basically containers? So so there are various architectures that comes into the comes into the picture. Traditionally, firms, they have monolithical servers where they have basically a single deployment framework, a server where they deploy their models. Nowadays, the trend has been moving towards microservices, where basically that's what I talked about. Basically, containers. Uh, each developer will basically create his own container, shape his own app in that container, and that will be deployed on the cloud. And another growing trend is using functions. Basically, this trend has been there growing for not bulk processing, basically, but small things or small function snippets, or basically single, for example, AWS Lambda, Google Cloud Functions. You might have deployed some models on these frameworks using serverless functions, where the entire basically pang of maintaining a server does not exist, and you transfer it to the basically the IT part, and the server part to the companies like Amazon or Google. So basically has been a growing trend. But does a developer have control over this framework? No, he doesn't. Basically, it's the firm's decision, and they set up their basically deployment framework, that okay, this is the architecture that we are going to follow. So at times, a developer is basically bound by that architecture that the firm has decided, and at times he's even bound by the toolkits that the firm has decided. So these are the things that stop a developer from taking that call on model deployment process. And also, and a major, and it's not like that the firms basically are happy with it. It's just because there are instances where you need specialized IT ops practices to basically support these new kind of frameworks, like containers and microservices. Uh, and a very good example is, for example, is Netflix. They have developed an entire field of chaos engineering to basically handle the testing and deployment on microservices. So you need specialized IT ops people to do that, and it is not possible for each and every firm to hire such specialized talents. So keeping that in mind, so we still have that question, that then what's the way forward? How can a user use the choice of his toolkit and still deliver and develop a model and ship it? So so that's what transitions us to the next step. So deployment is not possible, but do we still have a method through which we can democratize the model development process at least? Yeah, we do. Suppose we have a model interchange in between M1, M2, M3, and M4. All these four models, they were converted into a form which can be easily deployed. That would have definitely solved our pang. So basically, now the developer was free to use the toolkit of his choice, and still he can develop cutting edge models and ship it easily. And for the ops people, it would be very easy to deploy these models, because they are given in a standardized model interchange format. So once the analytical models have been created by the team, the process to operationalize them is lengthy and labor intensive. Hence, there are need for open standards to basically open standards for model interchange, through which they can communicate with the ops team and ship and deploy the model as soon as possible. So this brings us to the next segment, which is, so what's the way to save and share a model? So how should we go about it? Once we have developed a model, how should we go about saving and sharing them? So we to start with the machine learning models, let's take a few steps back and see how we are doing this data exchange and serialization for actual data. So we are all familiar with CSV format. It is the one of the most popular formats used for exchanging data, and we have seen how robust it is, and a lot of be it any toolkit, it has the inbuilt capability to read CSV files and process them. And a lot of other formats emerged since CSV format was tabular in nature. A lot of formats emerged which can handle unstructured data like XML, JSON, YAML. So JSON is one of the most used format for unstructured data, and it is the data of the web, data exchange format of the web. We all our APIs and all our basically apps, they use JSON. Web apps, they use JSON to transfer data and transmit data and process them. So it is one of the, it has widespread support. It is human readable, but there are disadvantages of JSON. Basically, it has limited data types, and there are some non-supported data types which are converted to string, and this has to be again dealt at the basically execution front, where you have to process such non-supported types. But so that was about talking about data. But but data is just a part of it. How do we actually serialize data structures and code objects? So data structures are like complex data types, and actually data structures which a programmer implements for his particular model. And code objects are like snippets of code which can be executed for the scoring engine part. So how do we do that? So basically, in programming, in a particular programming language like Python, Java, Ruby, R, we have some inbuilt serialization there. We all have used the pickle format, basically pickling Python code, and there is Java serialization there. Then there, for R, there is RDS and RDF formats. So these are built-in serialization format, but and it supports complex types and code objects. But there are disadvantages of using it too, as they can be malicious if they come from untrusted source. And also there is language locking. You cannot create a pickle and the pickle file and then read it using Java, or create a RDS file in R and then process it in basically Python. So a lot of basically so the language for processing such uh, serialized formats is fixed. So that is one of the major disadvantages of these inbuilt serialization methods. But what has happened is, due to big data, a lot of new serialization formats have emerged, which are efficient, and they are language neutral. So, and also they are platform neutral. So some of these formats, for example, a very famous format is SDF5, and then there are new age formats like Avro, Protoprof, Thrift. So these are some of the new formats which has emerged due to big data, and they are language neutral and efficient. So we can look into such kind of format to actually create our model interchange format. And this is the current landscape of the model exchange serialization in machine learning, which is going on. For example, if you are using scikit-learn, or you are using TensorFlow or R to develop a model. In scikit-learn, you can create a pickle file or a joblib. In Keras, you can export your model as H5 format. In TensorFlow, you can do it as basically flat buffer, saved model format. Or in R, you can create an RDA format. But a major issue is a major issue that is undergoing is this these libraries and this entire field itself is evolving so rapidly that if you are stuck with a framework which for example, Keras last year, Keras suddenly said that okay, it is now dropping all supports for other frameworks and going by TensorFlow itself. Then Theano also said that they are deprecating, basically they are no longer in active development. Cafet also said that okay, we are now shutting down and everything has to be shifted into PyTorch. So the whole field is evolving so rapidly that you cannot afford to get stuck with a particular format or a particular framework, and you need a language neutral, framework neutral way of saving a model, so that you can ensure they can be reused in the future. And this is, and so there is a need for developing standards, and this XKCD comic basically encapsulate how standards proliferate. And basically there are situations where there are competing standards, and then they say that okay, we need a new standard, and then there are 15 competing standards. So this is one of the reason standards are very tricky, and you need to ensure that, okay, there has to be a momentum towards a particular standard, and so that basically you ensure that, okay, this should be the industry standard.
We
So
have
there are model.
3 minutes left,
Yeah,
Ankit.
just a few slides left. Yeah. So there are few interchange formats like PMML, NNEF, ONNX, and PFA. So these are some of the interchange formats which are currently in development, and people are and there's an entire specification developed for them. Then there are a few formats for which there is no specification. So we will not talk about them, since only with the specifications and a particular majority of people going towards a particular standard, that is important. So one such standard is PMML, where you can use different frameworks and export their model using different libraries, and then create a PMML file which can be deployed. Uh, Another standard is like PFA, in which I also work. So you can create a model in R or Python, and then you can export it into PFA and ship it into Java, deploy it in Java or Python servers. And then there is an ONNX. So this is a very latest standard which has gained a lot of industry traction. So basically in ONNX, it's a standard for exchanging neural networks. So you can develop a neural network model using any of the frameworks and then ship it as an ONNX file, which can be deployed on any hardware or software. Basically, so this ONNX format is gaining a lot of traction. So you can see how it works. So if you maintain individual exporters and scoring engines for each and every format, you have to maintain around n square libraries. But using a standard ONNX interchange format, you just need to maintain one library for score, basically for scoring the model, and each and every framework, they will just export the model into that particular ONNX file. So another competing is NNEF, which says that it is complementary to ONNX, but actually it is not. It is one of the competing standards, and it has not gained that much traction. So ONNX has been the go-to framework for deploying for exporting deep learning models and deploying them at the edge. So I'll just show you a bit about Titus 2. So this is an example framework library that I developed, and this basically is based on a PFA format. And just to show you how this exchange format looks, let's take a look at it. So yeah, so you can, for example, let's say a particular very simple model. So there's a very simple model which is expressed in the form of a JSON. You can have an input data type, an output data type, and the action that you want to perform on for that particular input to get the output. A complex example is here, where basically you have different types. This is a complex structure, which is a planet which has a record data type. Basically you have different, it's like representing a row of data, and then you can perform you specify the input as a complex type and the output as another complex type, and you can do all the computation in the action part and then get the result. So this is a sample PFA data, basically data interchange file. And to basically just, you can have a quick look at PFA, which is readable. ONNX, basically ONNX files are not readable. So PFA is a good example to actually get a readable way to look how model interchange actually happens. So you can see the PFA specification in the PFA part, that you have an input, output, and the actions that you want to perform on the data. Then you have memory, also shared memory, and how you keep a track of the new inputs and the current output. So you can have a look at this part. And yeah, if you have any questions, just post it on our Discord group, and yeah, we are good to go.